Okay, the record is on. So let us back up a little bit and revisit the problem from the beginning. Okay, I think we have done the reactions and stuff. Okay, the main issue of this particular example is that we have this load that is neither perpendicular nor parallel to the member, so we have to do something about it. At the beginning, we have solved the unknowns, which are the reactions. We have them, and we start writing the free body diagram. Okay. Now, I think last time we finished member AB, and now we are at member BC. Now, I think this should not be a big deal to those of you who can see how coordinate system works. Okay. Do you know what we call this system in English, the XY coordinate? Anyone can recall? Now we have the uncomfortable silence because nobody knows what it's called. It's called Cartesian system. Remember? Actually, it's from your high school, you know. Don't ask me because I would not have remembered, but because I teach. So, okay. It's called Cartesian system. What you should recognize is that you have a choice. You can solve for n moments of member BC by using this coordinate system, the typical XY. Okay? You don't have to rotate your coordinate system into the local one. Let me call that, let's say, maybe I use different color to make it more distinguishable. X prime or Y prime. Okay. You don't need to solve for equilibrium in this X prime, Y prime universe. You can solve everything from the typical XY universe. That means you can easily solve for this. Orange, I use orange. This force by, sorry, it's not very straight. By using your typical sigma Fy equal to 0. You can get that because it doesn't matter where you look at your member. Okay, if you pick one coordinate system, and in this case it's typical XY, it should give you equilibrium. Or you can choose to solve this equilibrium in the X prime, Y prime universe as well. Either one should give you the equilibrium, but the force is going to be different because you rotate the axes, right? Now that's what you should know. The singular is axis, right? But when there is more than one axis, it becomes plural. So we change the I into E, that's a plural form, and pronounce axes. Okay, that's a plural form. Just like an axe that yeah, you use to chop people. Yeah, axis. But more than one axe, we pronounce axis, right? But this is axes. Okay. So without further ado, you can use your sigma Fy equal to 0, and this load is how much we have here is 3 tons per meter, and the total length in the x direction is 6 meters, so that's 18, right? Total. So from sigma Fy equal to 0, I have a problem calling names, so you have to forgive me if I use something strange. But anyway, VC is of course equal to 6 multiplied by 3 minus 8.1. So that's 9.9. So now we know this is 9.9 tons. Okay. Again, we can use this XY coordinate system to solve the moment as well. So we can take sigma MC equal to 0, that's fine. Let's say you don't know 9.9. You can take sigma MC equal to 0, and you will know your MC as well. That is going to be equal to, see, you can be comfortable with this. Let's say you think the moment generated by this 8.1 load is going to be more than the moment generated by the uniform load. So you can set up your equation like this. MC is going to be equal to 8.1 multiplied by the distance, that has to be 6, right? The distance perpendicular to your force, minus 3/6 squared over 2. That's this term, of course. I should be more helpful in this. This term comes from this uniform load, right? 3 multiplied by 6, that's a total load, and then 3 multiplied by 6, that's total load, and then multiplied by the moment arm, which is 6/2. So in general, it's a form of WL squared over 2. Okay. Let us repeat it here somewhere. Always when you have a uniform load on any length L, say this is W, and you take the moment at any end, the load is WL, right? So you can say this is a resultant, and the moment arm becomes L/2. That's why the form is always WL squared over 2. And now you've been this far in your journey to becoming a civil engineer, you should be familiar with this kind of thing. And funny how I should put it on the record that I just had a meeting with the committee, the curriculum committee, and people in the committee will be myself, Ajahn Chulapot, Ajahn Rumadi, Dr. Goran, and Ajahn Thongchai, for example. And we always talk about how students perform in the curriculum, and I complain because I've seen the exam, and I complain. It's not that I complain. I inform them that students don't believe in the free body diagram, because you have the free body diagram and then you do not write the shear force diagram and bending moment diagram according to your free body diagram. And Ajahn Chulapot informed right away that he said so many times in the class that, you see, the value did not begin from 0, and out of, say, familiarity or out of ignorance, we always start with drawing everything from 0. And now we are in the frame where you have n moments, so your most of the time the bending moment diagram doesn't have to start from 0 because we have n moments. And Ajahn Rumadi also informed that you don't realize that you can draw free body diagram of structure that is related to water as well. You can draw free body diagram on water because force can act on water, like pressure, weight, those kind of things. So it's not just about the class of structure that, okay, we need to treat free body diagram so and so. No matter where you go, you need to treat the free body diagram. And believe you me, you're going to face that in soil mechanics, because the one thing that concerns the soil is the stress. And now you have the stress due to the soil, stress due to the lateral pressure of the soil, and stress due to water in the soil. So it's the same thing, because everything will be based on free body diagram. So it doesn't matter where you go, as long as you can treat equilibrium correctly and effectively, precisely, accurately, whatever, just find the adjective, you'll be fine. Okay. So here we are. We will have MC equal to this is minus, because I think 8 multiplied by 6 is 48. This is 36, so this is more, so it comes out negative. Am I right? Could you please check for me? Is it negative? Yeah, I suppose. So my guess is wrong. And when you guess like this, you guess 8.1 is more, but it's less. So that means the moment will have to help it, and that's your MC 5.4 ton meter. Okay. So that becomes your equilibrium. You ask me if this equilibrium is correct. The answer is yes. But you cannot use this equilibrium to draw or to obtain shear force and bending moment diagram, because you now have the uniform load that is not actually perpendicular to the member. So we need to do something about it. Okay. So now, this is the one system that is under equilibrium, and you realize that from this system, your external load, let's calculate, your external load here, is a uniform load, is vertical. It's a vertical load. So in this system, it's not surprising that you have only the reactions in the vertical directions. You don't have the force in the horizontal direction because there is nothing in that, correct? So this is in imperfect equilibrium plus the moment. But when you change the system into the new coordinate system, because we need the force that is going to be perpendicular to the member, you have to turn this. Let's use this. You have to turn this load into the load that is perpendicular to the system. And now we are going to use a crazy little thing called trigonometry. Okay? And please, I think it's the good old story that I've been here 15 years, and you know, most of the time students don't really love trigonometry. So I find that a little bit amusing, because you study engineering, huh? And you hate trigonometry, so yeah, that doesn't go very well. So let's say I will okay, I'll use this angle. So I'll call that's my theta. Okay, if this is theta, you know, which one is theta when you want to use to turn this 8.1 into the one that is perpendicular to your member? If this is theta, what's going to be theta? That is the one thing that you have to do, and then many cannot. Funny how this, right? Do you agree? The easiest thing to see from this is that if you call this theta, okay, this is 90 degrees, correct? This is also 90 degrees. So we have two 90 degrees here. So if that is theta, that has to be theta, because they share the same angle there. Simple, right? Or you can use a more noble approach, but I think you guys are making notes. I'm just going to wait for a minute. That is the easiest one, the easiest approach for students who cannot use their imagination. Okay. They share the 90-degree angle. Let me try to redraw this again, maybe see if it helps. Okay, if we have this, okay, and I call this theta. Okay, we know that this is 90 degrees. Okay, and then I draw another line perpendicular to that line. And we also know that this is 90 degrees. So that angle is the same, right? So which means if both are 90 degrees, if that's theta, out of this 90-degree angle, this has to be theta as well. Can you see that? Or you can see that how you can rotate your member, you know? You can try to see this member. You want to rotate it to the horizontal line. How much the angle that it is going to twist. So it's basically this frame, you know, turning with that angle so that it can move from here to the horizontal line. And this line will move from here to that. So they move with the same angle. It's a more noble approach because you need to be able to see how things move. And actually, my advisor does that. He just, okay, this is rotate this angle. So this is that angle. So I said that. Okay. One of the way, but you can use trigonometry this way. to achieve the same thing. So now we know. That means we know that the new force in this angle will have to be 8.1 cosine theta, correct? I say this every year, so I have to say it again. That you know the word sine, cosine, tangent. Do you know the origin of these words? What languages are they? Sine, cosine, tangent, cotangent. Do you know what language is that? You can guess, but you will not guess it correctly. It's Indian dialect. So India, you know, was the first country to have discovered trigonometry. Wow. Yeah. Right. Okay. But look at this angle. Let me. Do I have a theta somewhere? This is an easy one for you. Let me scroll back up to show you, because this is your angle, right? So we use this similar triangle, but we have 6 and 6 here. So it's 6 and 6. This becomes 6 square root 2. So the angle is 45 degrees. You're not going to be that lucky, right? Because 45 degrees is like, it's for kids, right? We grown-ups don't do 45 degrees, right? And please, you know, the worst thing that happened a long time ago is that some students did not recognize that sine 45 is equal to cos 45. Please don't break my heart like that. All right. Okay, so now if this is cosine, that means this guy will be 8.1 sine theta. Okay, sine 45. And now we're going to look at the force. I think some of you still make notes, right? You may want to say, try to write more information here, that this is 8.1, the original force, and that is your angle. So you know 8.1 cosine theta will give you the force perpendicular to your member, and 8.1 sine theta will give you the force parallel to your member. You see, we haven't done anything very drastic at all. And right here, if you want to proceed, you have 9.9. So this is going to be 9.9 cosine theta. I keep writing theta, but you now know it's a 45 degree, right? And then the one parallel to the member is here is 9.9 sine theta. Okay. But what you will not get from this is the maximum moment in the member if you don't rotate your uniform load. Right. I think the space is pretty tight. You guys are making notes, so I'm just going to try to do this. Ready? Are we ready and willing? Maybe not much. Okay, so I'm going to scroll up a little bit. Now we know the total force here. You have to be careful because you can use the total force, the resultant force of the uniform load at times to calculate reactions, for example. But in drawing the diagrams, you know, you cannot use them. Okay, because you change the nature of the load. But however, in this case, we now know the total force is 18. Correct? It's from 6 multiplied by 3, or 3 multiplied by 6, and put it. So the total force is 18. This is the vertical one. We can do the same thing by turning this into the force perpendicular to the member. and parallel to the member. Right? That's going to be the fun part because you need to manipulate your angle again. And likewise, you can maybe extend this here. I'm trying to be as helpful as I can. So let's say, okay, so I'm extending this line. Now you know this is your theta, correct? Just look first. Some of your friends still are writing something. So could you please look at the screen, or you need more time? Let me know. Okay. The best thing about being in the class that I can see your progress. If you're still making something, I know I have to wait. But let's say if those of you who do things become less and less, and most of you guys sit still, I am obliged to proceed because the rest that are already finished the job, they become restless, right? And then when they wait for me to speak something and then I don't, they will start talking because they think I don't have anything to do anymore. So please, okay, take glasses off again. Now you see, if I extend this line, now we use this angle, so we know this is the angle, correct? And again, using the 90 degree to the maximum purposes, you know this is 90. Here is 90. So this is 90 minus theta. And that's 90. So that means this is theta, correct? You see that? This is theta. That angle is theta. Because this is theta. This angle is 90 minus theta. This is 90. So that has to be theta. See? Don't? Okay. So that means if I move from here, I'll try to move this thing out of the way. Okay. Now, let me redraw this again. We have the uniform load. The total, oops, sorry. Right. I have to, that becomes problematic. I know I can rotate it, right? But it's not going to be very convenient. Now we have this. You know the total in the vertical direction is 80. So that means the total load from the uniform load in the direction perpendicular to the member, or this direction, change the color. This has to be 18 cosine theta, right? Whatever we do, we cannot change the load. So you have to make sure that the total load is the same. But now it becomes a total load that is perpendicular to the member. So it's 18 cosine theta. And then of course you would have the another one here. That's 18 sine theta. But you should know by now that 18 sine theta will be the uniform load that will be parallel to the member. So it doesn't generate shear or bending moment. Okay? So now you know the total load here is 18 cosine theta, which is equal to, do I have the numbers multiplied by 0.707, right? No, I don't have it. So that's fine. Now, the catch is this. We know the total load, but the nature of the load is the uniform load. So we must maintain that nature. You remember? We see that we have to maintain this total load. It's 18 cosine theta, but we have to turn it back to uniform load because that is the nature of the load itself. So from total load here, you have to divide the length of the member to turn this into the uniform load. So here, the length of the member is 6 square root 2. So this uniform load that will act on your member oh geez, space is so tight. Okay. Call is W prime. W prime will be the total load in the direction perpendicular to the member, which is 18 cosine theta, divided by the length of the member, which is 6 square root 2. And cosine theta itself is 1 over square root 2, right? So it is 18 multiplied by 1 over square root 2, and then 1 over 6 square root 2. That is 1.5 ton per meter. So we are done in terms of the free body diagram. Okay. And let me give you the number here as well. But let you guys write this down. Okay, you'll be ready. Don't forget to have this as well. 8.1 cosine theta, that's 5.73 tons. And 9.9 cosine theta, that's 7 tons. Okay. If you want to try to obtain the free body diagram of this member in this x prime y prime coordinate system, you know, the one that is perpendicular and parallel to the member, you will find that the moment that you have here will be exactly 5.4. Okay, that doesn't change because you rotate the moment around the x-axis, which goes out of the plane. So the moment will not change. Okay. All right. Remember, we have the two equilibrium in one typical xy axis and another in x prime y prime axis, which are parallel and perpendicular to the member itself. So you can use the typical equilibrium from the first one to try to solve member CD. Okay, now recall that we already have 9.9 and 5.4, so you can use them to solve member CD. Okay, and as usual, I will try to finish the free body diagram of everything first before I finish the shear force and bending moment diagram, just to make sure that we have good system, correct system. All right. So member CD now. Okay. We have, see, 5.4 here and 9.9. 9.9 goes up So this has to come down, right? And this is clockwise, so this better be counterclockwise. Now don't be confused. If you look at the member BC in the typical XY coordinate system here, this is your forces that will put your member in equilibrium. So that means, you see, we don't have the horizontal forces at the ends, right? So that means when we come to member CD, that should not be the horizontal forces at the end as well. Even though when you rotate the axis to this one, you have the horizontal force. But that's different coordinate system. Be mindful of that. In the typical XY, you don't, but in the X prime, Y prime, which you need for your bending moment and shear force diagram, and so on, so you will have it. And this is not finished yet. Just for those of you who are curious, if you say you have the uniform load in the direction perpendicular to this member, you actually have this as well, the uniform axial load. But they don't contribute. It doesn't contribute to your shear force or bending moment diagram. So you can write it for your completion, but if you don't, I will not be so cruel to say, hey, your free body diagram is wrong, and you're done for. Okay? And it's the same number because of the 45 degrees, so that is also 1.5 ton-meter of uniform axial load. Okay? We are gonna stop a little late because we start like 15 minutes late, okay? So there you are, member CD. Are you catching up? So here, to complete our free body diagram, it's 99.9 over there. But again, some of you will be a little careless and think that MD will be 5.4, right? It isn't. Right? This is going to be what? It has to be in that direction, right? And here MD will have to be equal to 5.4 plus the moment generated by that one. Correct? Now you have any moment of 5.4 ton-meter and the shear force, which will add the bending moment to the system. So it has to be plus 9.9 multiplied by the length of the member, which is 4 meters. Don't forget that. If you forget it, you cannot close your diagrams for sure. Okay? It has to be multiplied by 4. And that is 45, ladies and gentlemen. And last one, okay? Member DA. Right here, you have 9.9 on joint D of member CD is going up, so this one comes down, which is going to match with our reaction of the system, right? Which is 9.9 at point E. So our sigma Fy is taken care of. And now we have the counterclockwise moment of 45. So this comes to clockwise moment of 45 ton-meter. Yes.
Why the moment at point D is counterclockwise? Isn't it?
Can you say again, moment at C or D?
D at red one. Why?
Right. I think you're right. It has to be clockwise, right?
Yeah.
My bad. Sorry. Yeah. Thank you very much.
thank you ครับ
Good. See, I don't really repeat what I do, and I don't even look at my notes. That's why I like to keep things fresh, no? So yeah, it has to be clockwise because when you take moment at D, both of these components will produce the counterclockwise moment. Thank you very much. So that means this. So you see, he's been paying attention. I feel very good, you know. So that has to be this. Otherwise, it will be busted because we have the reaction here, 6, right? And it's going to be matched with the external load here, that is 6. So everything is blue here. Let me change the color a little bit so that we know this is the external applied load, 6 ton here. That's a reaction of the system, right? So maybe to let you know that these are the reactions. Maybe we can turn that into something like green, like that. You know that these two are the reactions, and they match up with the forces that we transfer from member CD. So if you really want to check, but you can take moment at D, and you know it's going to be 6 multiplied by 7.5. It's the length of the member, right? That's 7.5. So 6 multiplied by 7.5, that's exactly 45. So voila, we have the perfect equilibrium. Okay. So I think I can finish this very easily before the break. So let us catch a break for you so that you can, you know, settle down and ready to draw the diagrams, which is like a piece of cake, right? Any questions? Maybe. We only have like 11 of you in the classroom. Yeah, I remember the first week, so like we almost have like 30, and we have 50 online. So roughly 1/3 is missing. And generally, you know, when one day some of you may be in my position, you know, being instructed and so on. So it's very easy to see when you grade the homework and exam who's in the class, who's not. And it's a sad thing because sometimes, you know, maturity is something that you don't have right away. You need to go through some personal experiences before you grow up. Some grow up quicker, some don't. I was a bad student. I grew up very slowly, and I really didn't know what I wanted to do after graduation. But we can talk about later on. Anyway, I think you guys are ready. So let us go back up here. First of all, member AB is just a column, so we don't need to draw any diagram for it, right? The most problematic one is member AB because we need to use this one. Okay, so let's get it out of the way. And I think I should redraw this picture somewhere else because it's getting a little bit, you know, say hairy over there. Okay, so member BC. You can write like this, you know, but I think I kind of write like that just to give the feeling that actually the member is inclined. You know? So we need to use this uniform though. Remember, must use the one perpendicular to the member. Okay, that is 1.5 ton per meter. Now you already know that this is 5.73. This is 7. And don't forget that we have a moment as well. 5.4 ton meter. And so your shear force diagram will begin in earnest with that number, right? 5.73. And it should come down to 7, -7. Shear force diagram in tons. You don't need to draw it in this, you know, angle, you know. But I kind of, you know, I'm old-fashioned in a way. You can just draw it in a straight line. It makes your life better. Anyway, so now we know that because AB is a leading column technically, so that means our bending moment will start from 0 in this case, right? And like always, that is the positive shear area. Okay, so your bending moment diagram should go up to the maximum value here. Okay, so before we do that, we need to calculate when the shear becomes 0, right? So that is going to be the question mark is going to be 5/73 divided by 1.5, which is the uniform load in this universe, so to speak. And we have the number, which is 3.82 meter. And from that, our maximum moment is just going to be equal to the area, the blue area, which is half of 5.73 multiplied by 3.82, right? So that is 10.94. So that number is 10.94. And you should pray that the negative shear area should bring everything down to minus 5.4. Okay. Are you catching up? According to our three-body diagram, right? And if you want to know that, I run out of the variable. Let's call it x. Okay. It should not be x because we use x for the system. But let's understand that. Okay, we use it just here. So we have, I think, the best way to calculate the point of inflection somewhere where m equal to 0, it's going to be by using the free-body diagram. So the moment is going to be equal to that shear force, right? 5.73 multiplied by x minus the uniform load 1.5 x squared over 2. Okay, and the moment if it's a point of inflection, this will become 0. To solve that, you get x equal to 7.64 meters, which is shorter than the length of the member. So it's correct. Can you read that? So I like a little bit thicker. You know, some your friend already helped change the thickness. Yeah. Okay. And got to write this. So this is our bending moment diagram in time meters. So we have all the information. That has to be minus 5.4. You can check that. Should come out to be like that. Okay, so we're done with that. Remember, without the uniform load that is perpendicular to the member, you will not get these diagrams. Okay, these diagrams are created by using the forces that will have to be perpendicular to your member. If you don't maneuver around the uniform load, you will use the uniform load that has both parallel and perpendicular components to calculate your shear and bending moment, which means it's wrong. Okay, we have a few more minutes, but I bet we can complete the shear force and bending moment diagram of the remaining two members with ease. Okay, so let me try to finish that. CD, piece of cake. You know, move this out of the way. Okay, you know, you see the shear. That's down and up. So you know right away the shear force diagram is minus 9.9, right? Negative area, shear force diagram. And bending moment diagram, both are negative. So you know from the preliminary diagram, it's like that. Wow. Can we have something like that? Can we have any moment diagram like that? That's minus 5.4 and that's minus 45. Negative as well. It's bending moment diagram. Of course you can, because look at member CD. There is no external force at all. It's just the member and the force at its ends. So the shear become constant. And the moment is just values of the end moments that you already have from your free body diagram, right? If you don't believe me, you can start here by minus 5.4 and then you can calculate the area of the shear force diagram. That will add up and give you 45, minus 45, right? And if now this member DE, I kind of prefer to stay inside the frame, so I'm just going to look from here. And when I look from there, my shear force is going to be positive, right? Because it starts with the grade 6, which goes up. When it goes up, it's a positive one. So that's positive shear force diagram. It's a little bit misleading, so I just bring it down. Okay. And the value here is called 6. And you have the positive shear area, but when you start from here on the left, that becomes a negative moment, right? So the negative moment of minus 45, and the positive shear area will bring this back to 0. So that's bending moment diagram. Simple as that. See, we begin from the left by looking from the left. So the positive shear area will bring negative bending moment diagram back to 0 at the hinge. Is it too quick? Bring back to 0.
Can
Yes.
I have a look at BC?
BC? Oh, you mean down there? Okay.
Okay,ครับ.
So folks are here to spare your friends a little bit. Maybe should I make it smaller so that you can see more? Or here,
Yes, it's better. It's better.
Like that.
Okay,ครับ.
And let me know if anyone wants me to scroll back up. Okay. So right on the mark, 10:35. We are a little bit late today. So there is a word in English. They say force majeure. It's French. It's force majeure. It's something that it's a force of nature. You know, it's like the accident that we just had. The computer broke down. There's something we can do, right? So when you run into the situation where you cannot help yourself, they declare force majeure. It's because of Mother Nature. You will see this word in some civil engineering contract. For sure. You may see it, you may not. So they say, in case of force majeure, you know, so in case of maybe if you build a building and then, you know, it got hit by the worst storm of the century, that becomes force majeure, and then it's not my fault that the building collapsed. It's force majeure. Or you build your hotel at the foot of the hill, and then the avalanche occurred, and it just all snow fall into your building. So we can declare, that's force majeure. It's not my fault. The hotel breaks down or the hotel collapses, something like that. So we had the force majeure about our road this morning. Okay. Anyway, is there any question? Do you want to scroll back up to see these two members? Yeah, actually, I can put everything together, but it's going to be a little bit small. Okay, guys, in that case, it's time to take a break. You want 15-minute break right away to have breakfast, or just 10 and then 15 later? Because if you want to have your 15-minute break now, when the second break is going to be 10, okay? 10 or 15. 10 and then 15, right? So come on, let's go. 10-minute break. Come back at 10:47. All right. Oh. Okay. You know what? Let me go back up. I want to know what happened. It's not my fault. No. Whenever I feel confident with the system, something always happens. Good night. Tin học được không? Tin học được không? Dạ phải bỏ thuộc ra phụ lừa ôi đây còn
ตรงนี้ก็สอนเองแฮโร่ไม่อยู่แล้วแฮโร่ประมาณ
ว่าไงเจมส์
I don't think it's really quick. So, okay. I don't know if this kind of thing keeps happening to me because I can handle it or what. I don't like it, And I really don't like technology. I'm old-fashioned. I love to read books, and the books I read must be books. I don't read Kindle. I can't. It has to be books that I can grab. I can feel its physical presence, something like that. And this is a good year for my reading. I've finished like 12 books already. That's quick, right? Anyway, so we are pretty finished with this example. So if you don't have any question, we can move on to the next example, I suppose. Oh, there, do you like that? This is really I inspired by the tunnel, something like that from soil mechanics. And if I can recall correctly, this is from the exam. So you're gonna see the exam like this. And I don't know, maybe this is from students and so and so. I didn't make it up. And they say that when they handle my exam, you have to have like a nerve of steel, because the first time you see my exam, you're gonna be spooked. You're gonna be surprised in a very exciting way. Oh, what the heck is that? So for those of you who get easily, shocked by something, you need to say, have a nerve of steel. But so you may ask, how can we have the nerve of steel, right? It comes from practice. Practice. If you have done a lot of work, I'm not saying that you need to solve like 2 million frames before you can do my exam, because just 4 or 5 will do. And I believe that if you are motivated enough, and you finish all the exercises that I have given you, the active session with your friends, by yourself, so and so. If you can finish all those things, you'll be okay with the exam. Chances are, because you think how many ways I can surprise you, right? So yeah, that's the thing. So when you look at this problem, how do you begin? One thing that it should not surprise you is that I tell you that in the world of determinate system, shape doesn't matter with the reactions. You still recall that? So it doesn't matter what shape I put in here. The reaction will not change. So it should be, the action of this frame should be very easy. Because if shape doesn't matter, can I draw something like that? Yeah, the reaction is the same, right? So without anything, you already solved the reactions. So now you know it's 2,400 kilograms per meter and the total length is 10 meters. So you know the reaction has to be equal without having to do anything. But then because some of you have not practiced enough, because you are lazy, and then you hope that you can find a miracle in the exam room. Miracle occurs, but not in the exam, if you don't practice enough. So see, reaction is done. You don't believe me? Well, it's symmetric, right? The load is symmetric. And whatever we have here doesn't matter. So then, there you go, reactions done. Right? And we can now start. Guys, if you don't believe me, you can take a moment, okay? Take it. If you don't believe me. But you choose to believe me because you're lazy. I know. So it's human nature, I am a little bit concerned because symmetry is something that I always emphasize every year. And my trickiness, so to speak, will give you something like symmetry, but make it a little bit, shrouded in something that you will not see directly. Especially in structural analysis, number 2, you get a lot of symmetry. And if you cannot take advantage of that, you will be problem. So because of symmetry of the load, and we know shape doesn't matter, so in the end, this is like a simple beam that got twisted at 2 points. So the structure becomes a little bit crooked. Okay, so the reaction is taken care of very quickly. So now, without further ado, we can start looking at the members. But before that, to avoid confusion, let's give some name, okay? A, B, C, and D. How do you like that? You like maybe Latin alphabet, alpha, beta, gamma, delta, perhaps not. Okay. And right, so we can try. Member AB reaction and the total load here. No, really. If you look at my notes, you see that you fold here. This is all I've done with this problem. You know, a quick scrap and that's it. Not that big of a deal. So, okay, I need to draw the uniform load. Yeah. And then again, to make our life a little easier, I know I can solve this in the XY coordinate system, so I can easily solve this reaction, right? That is 6 meters, so the total load here, let me move this out of the way. Okay. Oh, somebody's ooh, okay. Folks at home, you don't hear that. Somebody's making a screeching noise. I forgot. Okay, so the total load here, let's just change the color. The total load here will be 2400 multiplied by 6, right? So that's how much? It's 14400. So that, you know, if you're lazy, you can use your sigma Fy with a 0, and you know that this is 2400 right away, right? See, that's total of 14,400. So you minus that with 12,000, you get the reaction very quickly. You want me to change the load into the load perpendicular to the member, or you want me to just finish the force at the end of the members first? Okay, yeah, as usual, nobody's answering me at all. It's like I'm sitting here all alone, talking to the wind. Right, all I see here is something that I thought were human beings, but then they just series of colors, you know, beautiful colors appearing before my eyes. Oh, the colors are moving, but they're not talking. So I'll do what I want, okay? It solves everyone's misery, right? So let's say we can try to solve for this moment, all right? So it's 11 here. I don't know. MB should be equal to 12,000. That's a reaction multiplied by the length, which is 6, right? We need this 6 because this is the distance perpendicular to the reaction. Okay. Then minus the moment due to the uniform load, which is 2400 multiplied by 6 squared over 2. You know, what I do is not difficult at all, but it just sometimes you don't have enough practice, so you can't catch up with me. I'm not the smart guy, but I'm the experienced guy. Question? Or you just colors before my eyes, right? You don't. Here? RB here? Oh. Hang on. We better be more careful, right? Is it this total? Is it 14? Let's use a calculator. I think it's more than half because you see it's symmetric, so that's 1200, correct? This is 6 meters. It's more than 5 meters. So that means this uniform load should be greater than the reaction, roughly speaking. right? So right here, VB, or you want to call it RB, it should go up, shouldn't it? Don't you think? It should go up, right? Because it's more than half the length. Let's use the calculator. 24 multiplied by 6. I like that you asked me. So don't worry if it's wrong or something. So let's do it together. The total force here, that's 2400 multiplied by 6. Hey, you asked me and you're not talking to me. I'm very sad. Am I correct? 2400 multiplied by 6, that's 14,400, which is more than this. So it has to go up, right? Otherwise, it's not equilibrium because your downward force is greater than this orange one. That is 14,400. So that should go up. Yeah. Okay. So now we take moment at B to figure out MB. So it's this reaction multiplied by 6, and then minus the moment due to the uniform. Okay, so that's 6 meters. And the number is 28800 kilogram meter. Yeah, right. Okay. So yeah, every year you're trying to imitate me in my style, but you should try to imitate my style in the exam as well. All right, let's do it. Do the exam, but like the way I do, make it cool. It's not that. When do we begin? I don't remember anymore. I don't remember when we should have a break. Anyway, so that is MB, ladies and gentlemen, right? And I think it's not a bad idea to try to finish the free diagram right away. So, all right. This, is 6. That is 4.5. So this is a similar, it's a triangle 3, 4, 5 system. I love it. 4.5, 6, so here is 7.5. Do you know 3, 4, 5 triangle? Right? There are only 3 triangles that you can, Okay, so we all know. Nice. Nice. I like 3, 4, 5 triangle. I really do. It's like, wow. It's a good ratio. So now we know this is your angle. So that becomes the angle again, right? So that means the total force here is 14400 multiplied by cosine, which is 450. Correct? The way you pronounce your fraction, okay, 4/5. Okay. If it's like this, it's 3/5. That is, geez. How do you pronounce that? 3/4, right? But I will pronounce 3/4. It's easier for me, right? 3/4 right? 3/4. So it's here is 4th. That is 5th. Okay, that's how you pronounce it. And this thing is called fraction. Okay, it's not structural engineering. I'm just going to erase it. Okay. All right. What? So that I don't know, but let's the total number here is, excuse me, okay, I can move it. So to make your life a little easier. Oops. Damn. Sorry. Pardon my French. Oops. It's getting absurd. Okay, at last. Okay, I think this is 11520. It's a total force. Remember that this is not the uniform load. You need to turn it back to uniform load by dividing this by the true length of the member, which is 7.5. So your uniform load here W prime is 11520 divided by 7.5, which is about 1536. Okay. And if that's the angle, this is the angle. So this force is 12,000 multiplied by cosine theta, which is 4/5. That's 96,000. And here, same angle. That one is 2,400 multiplied by 4/5, which is 1920. And the moment remains the same. Just like the song remains the same. Let's separate. Yeah. 28800. So we have a complete fluidity diagram. You know what? I forgot to give you more examples, maybe. I don't know if I have done that. Anyway, we will work on this. Because do you have example number 9 and 10 already? It's for supplement. Yes or no? Maybe not. So I forgot. My bad. But let's finish this first. Okay. Now that's done. We can leave it like that, and now we can go back to okay. Maybe I should write that this is member AB. Now the trick is with this. If you know that you can find the equilibrium with the typical XY axes, you can easily complete the free body diagram of member BC and C. Where's D? Where's D? I thought I wrote it. Somebody erased my D. Who? Should it be me, right? I don't believe it. Okay. Anyway, so we can easily obtain member BC, you know. That is your free body diagram, and your uniform load this time is already perpendicular to this, so we don't have to do anything about it. And you can take this force from the NB of member AB. So let me try to change the color so that you know these forces come from member AB. So it goes up. So this one comes down, right? And you have counterclockwise moment there, so you have clockwise moment here. be very careful because sometimes when you get used to the number, okay, this is 2400, the total force is 48, so that's 24. So you think, okay, that's another 24. I'm sorry, because it's 48, the total force is coming down, right? So in fact, this is going to be equal to 2400 plus 2400 multiplied by 2, which is 72. Okay. And say MC, yeah, it's going to be equal to I think it's going to be this clockwise because that's a big moment. 28,800, that's moment MB minus 2,400, which is the shear force, and that's 2 meters, right? Multiplied by 2, and then minus 2,400, which is the uniform load, multiplied by 2 square over 2. And the number here is 19200 kilogram meter. That's done in the BC. He's a kid, right? So far, you would feel sorry that if you missed something, you know, in the exam or something like that, because after all, it's a test of equilibrium. Whether you can actually find the correct equilibrium for any given system. And now we're just in the determinate system. That means you can always solve for the reactions of the system and then, you know, proceed to obtain proper Fibonacci diagram. All right. So we are now left with the last number. Just, let me give some space for the shear force and bending moment diagram of that thing. Last one of this system. So now you realize that this is where everything comes together. So some will say, okay, now I know the reactions, now I know the force from BC. I'm not going to do anything. I'm just going to fill in the gaps, right? But here you can do that. But if you have something wrong, you know, your easy job will turn into something awful. So that is the reaction. And here you have 72 going up. So this one comes down. 7,200. So it's time to check whether or not this, you already have two forces at both ends, right? It's time to check whether or not they are correct. Reaction should be correct. So you pray that, okay, oh, sorry, that line is so ugly. Okay, the total force here is, of course, that's 2 meters, so it's a 2,400. So you have total force 2,400. That's a uniform load, right? Yeah. So the total force here is 48. Right. So total force of 4,800 plus that, that's 12,000. So we are in a good shape, right? At least our sigma of y is satisfied by all the forces that we put together without solving anything. So we should be at least a little bit happier, right? And now you have this moment from member BC. That one is counterclockwise, so this one better be clockwise by the same amount. So you take the moment, and if it turns out to be okay, then we are good, right? So check sigma moment. But I know it's correct, but I'm not going to do anything. Should I? Should I not? Why don't you check it? Check me. Right? Check me, not check me. Now, speaking about that, there is a huge news in the world that they say chess players cheat. The world champion said that the person who beat him cheated him. I don't know how you can cheat in chess. How? It just baffles me. Anyway, so I suppose the only thing left to complete this free-body diagram is to turn this uniform load into the uniform load that is perpendicular to the member. So it's business as usual. Okay, we go back and try to obtain this. Ooh la la, look at that. 1.5 and 2. So that's another 3, 4, 5 triangle, right? I told you I like it. So that's 3, that's 4, that's 5. So if that's 1.5, that's 2, the length is 2.5, right? Simple as that. So okay, same thing. We know the total force. If we know that that is the angle, we know that's going to be the angle. Okay, so now you can perhaps do it very quickly. That the W prime is going to be 2400 multiplied by 2. That is your total force of 4800, right? Multiply by cosine, which is 450, and then divide by the true length of the member, which is 2.5. If you're not comfortable with this, you can try to, okay, maybe you write this term first. That this term is this force, just so you see the picture that, okay, now you have the force perpendicular to the member, then you divide it by the true length of the member to obtain the uniform load that is perpendicular to it. Okay. So unsurprisingly, because the angle is the same, the uniform load is the same. So when we write it like this, our system is in fact, oops. The uniform load is the same. Number. Okay. It's the same. And now when you know that that is the angle, so this is the angle. So here is 12,000 cosine theta, which is cosine is 450. So that is 9,600. Okay, and here that's another, but it's downward. This guy is 7,200 cosine theta, which is 5,760. Oh, did we forget something? We have to have both. That's it. Complete free-body diagram. The rest is easy now. Okay. We should have like 15 minutes to finish this, bro. Okay. So we will go back here. Now, you know, you need time to write something. Okay, I should scroll back now. Maybe give you a minute more. So. Oh. It's very funny. Sorry, fine. This is going to be a joke in Thai language. It's not a joke, but you know, yesterday I saw a lot of posts on Facebook. Rak mi chai duong nan kind of thing. I didn't know what's going on. So I asked my wife this morning. No. Do you know that it's a very famous song? I was perhaps like 10 years old when the song came out. You should try to find that song, listen to it, because it's a beautiful song. I think it's beautifully written, and it's like everything rhymes. Back then, you know, when they compose music back then, they always rhyme. But now they don't care anymore, and the melodies are kind of beautiful. And the band was named like girls. That sounds. Or ladies. Just like it kind of evokes the old memory, because the song came out when I was really 10 years old. And back then there was only a cassette tape, you know, and it's like a classic era because I listened to radio. The cassettes were not very that much popular. You have to go out and buy them. Most of the time people listen to radio. You could not imagine, right? But now you have the internet radio. It's pretty much the same thing, I suppose. But what you could not imagine is that, can you think about TV without remote? Every time you want to change the channel, you have to walk to it. So, you know what happens in my family? The kids become the remote control for the parents. So it's kind of very funny, right? Because when my dad wanted to change the channel, he would call for one of his kids, "Hey, go change the channel," and we would be extremely upset because we would be doing something else, like reading cartoon, and we gotta get up to change the channel. But fortunately, there were only like 4 channels available back then, so it was okay. There was no such thing as cable TV, you know. Anyway, let's finish this. So you should know by now that once you have all the n forces solved, this is a piece of cake. Because let's suppose that you check and all the numbers are correct. You can just start drawing the shear force diagram very easily. It is going to be 9600, right? And I still, you know what? I'm sick of doing this, so I'm just going to do this. Okay. It's going to be big. And you know, one thing that I always tell you guys to do every year, your students, your senior, is that whenever you draw something, try to draw it to a true scale as possible. It will help you. For example, if you know this is 9600, okay, and that is 1920. Oops, how did I do that? 1920. This is supposed to be bigger, like that. Many will not pay attention and draw them equally. And when you draw things to a better scale, you would realize that this area is way bigger than the negative area there. So it's only natural that when you draw your bending moment diagram, you know, things may be perhaps because the positive area is so huge, this will not become negative after all. And it's, yes, because look at your end moment, 28,800. And look at the sign. That's a sign of the positive moment, right? Remember, on the right, counterclockwise, that's positive moment. And it shows from your shear force diagram because you have a lot bigger positive area than the negative one. And in fact, from the true length of 7.5 meters, if you try to solve for this x is 9600 divided by 1536. That is 6.25. So out of 7.5, this is like 6.25 already. Right here is only 1.25 meters. So it's a very small area. So, you end up with a positive moment at the end. So now all you have to do is trust your calculation and free body diagram. Someone, we don't suppose you have a diagram like this. No, not anymore. This is a frame. Okay? And you'll know by now that positive shear area will give you this value here. Sorry. Say, okay, like that. And that of course is M positive is no, not M, not enough. M positive max is a half of 9600 multiplied by 6.25, which is turns out to be a beautiful number, 30,000. And that number is from the free body diagram. You don't have to do anything if you don't want to, and if it's correct, right? But you should check. But you see it. Oh, 1 minute. My daughter calls. You may wonder why I talk to my son in English. Is it because we are in the class that I talk to my son in English? Actually, no, because he's very good at English. 10 years old. And he's not going to an international school, he's just going to Thai school. But because, we just a very small family, so I'll let them play whatever they want. So he plays games. And when he runs into something he cannot solve, he always has to find solutions on the internet, and all the solutions are in English. So he listens to English every day. So see, English is not a difficult subject if you put your mind to it. He's only 10 years old. He has so many crazy vocabularies in his head. And I can say that my kids listening are better than mine because they grew up listening to YouTube and Cartoon Network and so and so. Sometimes I have a hearing problem because of rock and roll. Sometimes I don't hear very clearly. But anyway, so here we have it. Any question about this? So this value comes down a little bit because of a negative value. Okay, and when you run into BC now, you see, BC is pretty straightforward because it's just like typical beam with the uniform load. But some of you will be so familiar with a simple beam. Remember, this is not a simple beam. It's a member. And if you really wish to draw something with the support, this should be it should be close to something like this, with the uniform load. But then again, they are not fixed supports because they move. They are rigid joints. So when you draw the diagram, you see that the shear here, it's down and up, so it means a negative shear, right? Oops, you know what? I'm wrong. Hang on, do you know why? So the constant, right? So that line is wrong. I think I have a pressure of running out of space. Okay, so let's draw it here. That is minus 2400. So it goes up on the right, which is a negative shear in the diagram. So that's your shear. Shear force diagram in kilogram force. And this is a negative area. So you know your bending moment diagram, that is positive, but both are positive, and I have to undo this because it's going to be closed. But here, you see, 2880 on the left, but you have the negative shear, so it brings your moment down to 19200. That's your bending moment diagram with a little bit small kilogram meter. Okay, so it makes sense. They are related. I have to admire because every time he wants to use something, he always seeks permission. My son, so he feels like he has to call me before he uses my computer. That's a good thing. Okay, so we're done with that. So again, this is simple because we have everything. Are you catching up? That's that, right? Too small. My apologies. Just want to squeeze them in. I hope you're fine. So we're done with the bending moment diagram, and now CD. Okay, we have a shear force diagram. I can just put them here. It's going to be tiny. See, it comes down with the uniform load, comes down and goes up. So it's a negative shear again. It looks like that. Okay. So that's minus 5,760 negative shear, and then minus 96,000. Okay. That's a shear force diagram in tons, and of course, bending moment diagram. Now we have end moment. You know what? It's I am pretty bad at managing space. Okay. The bending moment diagram here in it's in kilogram, right? Not tons. Kilogram force. This kilogram meter. So the bending moment diagram, we start from the positive moment here, and then it should go down to 0. Simple as that. Were you done quickly? Wow, your friend is finished. He's playing the mobile phone now. I'm in a hurry. Or maybe it just went lazy for a moment. And then he's finished. I better be quickly. I better move quickly. And then everybody is trouble. Right? Hey, ask me questions. Come on. Piece of cake, right? Easy. Yeah, red shoe. At one time, I wanted to wear yellow shoes. My wife sort of like, like the one that Uma Thurman wore in Kill Bill, yellow Onitsuka tiger. That would be cool. Okay. Anyway. Before we take another break, I will let you see this. If you put bending moment diagram of them and shear force diagram of them together, because I draw everything in one page, I can see that. You see the nature of shear force diagram here. Also, shear force diagram here and here and here, and then bending moment diagram here and here and here. If I put them all together, you know what I'm going to get? it's like a simple beam, you know. See, I can put them together. This guy, that guy, and then that guy. Right? But the shear may not be of the same number because we have to move the load. But the nature is that this is just a simple beam, but I just kind of give it a twist to have your to give a little fun into your humdrum life, you know. So the shear may not be as conspicuous, but the bending moment is apparently like that, right? Yeah, but in order to do that, you need to do a little things. Okay, so that's just a problem. So for those of you who just get spooked very easily, you see the problem. Oh, what is that? Oh, they took in high numbers and so and so. And they spend like 10 minutes panicking. In fact, it's nothing. So the point is, you can overcome the spookiness by practice. When you see a lot of things, when your world become a little bit more expanded, these things cannot trouble you. And these are the things that you face in the real world. Because nobody builds a block, right? We build the structure with so many shapes. Okay, and yes, unless you want about every time, right, that we interview you guys, hey, why do you want to study civil engineering? And then every freaking time, your senior will tell you, hey, when the teacher asks you this, you answer, I want to build my own house, something like that. So that's why if anyone has been interviewed by me, you will never hear a question like that. I'm bored to death with the answer. But you guys haven't seen me in the interview, right? So yeah, unless you ask civil engineers about to build your own house. And if you want to build your own house, according to your so-called dream, your house will look like this, right? Yeah, that's gonna be your house. Because why do I want to calculate the difficult beam? I would use a simple beam, right? That's gonna be your house. Oh, and really? Oh, do we really need to have a lot of rooms? No, I don't want to have a lot of beams to support the walls. I don't want to be like that. And oh, really? Do we need to have windows? If you want to have windows, you need to break the wall. You need to put the small beams to support the window frame. So let's not have a wall. Why? I leave the box. So that is your life without architects. And then one day, one high architect will try to just, oh, why don't we have a little bit of cantilever here so that you can have a veranda that you go out, watch the moon, during the moonlit night, enjoy the moon with your say spouse, your husband, your wife, your kids. And then, okay, in order to have this veranda, you need to have an overhanging beam, cantilever, and so and so. And then, no, I don't want to calculate this. You have a negative moment, so and so. And then, I remember from the structural analysis class, I need to have this beam and then supported by that one. No, I don't want to do that. So no, I don't want to see the moon, so and so. So yes, that's what it is. Okay, it's time to have a 15-minute break. And I think we run out of our example. I have more, but I haven't given it to you. So I'll try to find it in here and try to post it on Facebook. Okay, while you have a break. So enjoy your break. See you in 15. Okay. I don't know if I can go through. Let's say. Oops. Hey,